I have a hard time imagining.
This looks like an heirloom.
So meanwhile, you realise you just signed a contract with COP.
Apologize. Well, we have to sign this contract with COP anyway.
That was a joke, actually.
We'll get back to work. I'm already falling far behind Peter, of course, in clarity and content and everything, but I guess it's no shame to fall behind, fall short of such a distinguished predecessor, so it's okay. Right. Now, okay. So I'll denote by something I'll attempt to make capital pi. The pro P a tau fundamental group of x bar with some base point at there should be a tau here. So let me explain again. So P here is a prime, and x is a variety over K, which now for concreteness I'm going to fix this to be a number field right at the beginning, and B is a geometric point. A lot of the time rational. And this, of course, refers to the maximal pro P quotient of pi 1 to tau x bar P. Okay. But of course, a lot of the theory will be independent of what I'm sorry? Oh no, this was supposed to be. Yeah, sorry about that. I was supposed to trying to include the tau, having forgotten for a second. But, that's right. So I should say tau, comma P. Like that. But I won't use that notation again because it's cumbersome. I'll just try to consistently denote the whole thing with a big pi. Okay, and this isn't so essential. I mean, even this assumption isn't essential, but again, for convenience, I'm going to assume that the abelianization, of course, is pi mod the closure of the commutator. Yeah. We'll assume that this is free, ZP module of rank, say, D. As I said, I'm not going to need this for a lot of the construction, but nevertheless,
this thing gets the projective limit topology. I'm not sure that you said this. It gets the projective limit topology, yeah, from this.
You mean the pi 1?
Yeah.
Yes, that's right.
Yeah.
That's right. Yeah. So, since in practice it's always going to be like this, I'm going to make the assumption at the beginning and then forget about it. But all the practice that I'm interested in for the time being. This. And so, now we're going to, this lambda is going to emerge again. In this case, also ZP is double bracket pi. Sorry?
Why is it free?
Oh, because I'm going to be interested in homology of curves.
No, this is a hypothesis.
Oh, this is a hypothesis.
Hypothesis, that's right, yeah. Sorry. Sorry about that, yeah. So this, as before, by definition, is the inverse limit of the group algebra Zp of C, where C runs through finite quotients. With the inverse limit topology, as before, as in Peter's discussion. This is the inverse limit topology. And if we do this, so lambda will become a compact topological, so therefore Hausdorff, that's just the usual convention, topological algebra.
Can you push up the board behind?
Oh, sure. I'll denote by epsilon the augmentation map. Okay. So what this is, recall, is that we'll have all these ZCs are ZPCs are equipped with the augmentation map to P that sums up the coefficient, and this is the inverse limit of this kind of augmentations. Sorry. The inverse limit of these maps. So, and by I, I'll denote the kernel of augmented. So I refer to this as the augmentation idea. Now, what's clear from the definition is that this is going to be the inverse limit of the augmentation ideal of C, where this, as I said, is just in words just now, is just defined by this exact sequence. So this is a closed compact ideal. And here's the lemma. I don't remember if, sorry. Lemma is that I is generated as a left ideal. Well, it's a bi ideal, of course, but as a left ideal is generated by, let's see. All right. Sorry, I should have introduced this notation before. Goes from 1 through D, where AI, this is a lift of a basis for pi abelian. Okay, so let me say this again. So recall that I was assuming up there the abelianization is a free ZP module of rank D. Just lift that to any collection of elements. Lift a basis for that to a collection of elements of pi. And then for that collection, you can generate elements in the augmentation ideal by taking AI minus the identity element of the group. Now I'm calling that alpha I. Sorry, too much into the notation at once. And so there are D of those, and those generate I as a left ideal. I forgot, did you prove this in your lecture already?
Not for topological generators of pi, not of
Well, I mean, I guess it's the same thing. This is a pro P situation, but okay, I guess I'll give a proof. Yeah. So proof is that. So let's see. Again, this kind of proof I'll also not do too many of, but just so we know what's going on, I guess we'll do one or two anyway. Sorry, first I'll call M. So I'll call this the sum over I of lambda AI, lambda alpha I. Yeah, so this is certainly contained inside the augmentation ideal. The lambda module, left lambda module generated by the alpha I. So we'll denote that by M. Okay. And to show that that's all of I. Let's see a finite quotient of pi. Okay. So this will be some finite P group. P group. Right. So if you look at C abelianization, so that will be a quotient of pi abelian. Pi is a quotient. C is a quotient of pi. So in particular, this implies, and this is a P group. So this implies that the class of the AIs, yeah, the classes inside C, generate C. This is a P group. So then, what do we want to write here? Now, but if you take a product, this is okay. If you take a product of elements like A I sub j minus E, product over j. Sorry, the other way around. Right. You take a product of elements like this and subtract E, then we can always write this as a sum is, if I get this right, so here j is going from say 1 through m for some product of elements. So this is an arbitrary element of C, that is. And then if you subtract E, you can always write this as k goes from 0 to m minus 1 of product of over j goes from 1 through k of the class of AI sub j times the class of AI k plus 1 minus 1. Sorry, minus E. So this is just an elementary assertion. Let me just write it down again over here for an example of this.
What is E?
Oh, E is the identity of the group, which I'm using for the group pi itself as well as its image in any one of the C's. That's my notation for the identity. So, for example, if you have say A1, A2 minus E, all I'm saying is that this can be written as A1 of A2 minus E plus I guess A1 minus E. This is correct, right? No, A1, A2 minus A1 plus A1 minus E. So this is an example, and you can just keep going in this way. So the general expression is this. And of course, these guys generate the augmentation ideal of C. The entire consistent is generated by these guys. So these will generate the augmentation ideal. So in other words, so image of M generates well, actually is equal. Sorry about that. The image of M is equal to the augmentation ideal for C in the previous notation. So this implies that M is dense in the augmentation ideal itself. But of course, this is just a finitely generated submodule of the ring. Yeah? So it's already closed. M is closed. It's compact, so it's closed. Implies the M is in fact hard. has a fairly simple description of this sort. Right. Now, suppose J1 and J2 are two ideals in lambda. I'll denote by J1, J2. Again, slightly confusing notation, so maybe I won't use this notation. So by this, I'll just denote the closure of the usual ideal. So closure of ideal product. And then when we take 3 of them or any collection of n of them, of course, we can do it in any order, just being, because the whole thing will be the closure of, again, the usual ideal product. So if you take, say, J1, J2, take closure of that and take J3 bar. And of course, this is just J1, J2, J3, so you don't have to, this operation is associative, so you don't have to worry about that. Now for a moment, I guess I need briefly to discuss this thing. So let's take a set of symbols, simply xi, as I goes from 1 through d. So this is just a set of letters. And denote by w, these are the words on xi. So they don't commute in particular, you just get any particular finite length word on xi. Remember also the set of generators, I wrote alpha I for this ai minus 1, there was this notation. So for any given word, I'll associate to it something, I'll write w of alpha. So this is the element of lambda obtained from the word by sending, so this is the image of w under map that sends xi to alpha I. So to say this precisely, I have to talk about the monoid of words and things like this. I will just say it slightly informally this way. Right. Okay. Then, if you take, so here's a lemma. If you take in bar, the closure of in, so this is generated as a left lambda module. By the set, I'll write it this way, Wn of alpha. This is a collection of W alpha. W is a words of length n. Okay. So the words in the alpha I is of length n, which generates the I. So it's just a well, in particular, in bar is just in. So once you have this assertion, it will be just a finitely generated lambda module. So that's just the same as taking the ideal product that's already closed. Once you have this assertion. Okay. So this is again elementary, similar to this computation here. Okay, so proof by induction on n. Yeah, well, we just proved it. We're done for n equals 1. So we just showed. So now we examine in plus 1. So we assume for in. Okay. And now let's examine in plus 1. Well, so if you we write in plus 1 as I times in, then we're writing in by the inductive assumption. So this will be a sum of products. This consists of sums of products of the following form. Oh, sorry. Yeah, let me write it this way. I want to say this. In plus 1 consists of sums of products of the following form. Summation over I of gi alpha I times summation of f w w alpha, as this runs over word of length n by the inductive hypothesis. We're assuming, sorry, I had to say like this is the length of a word. We already assumed that I to the n can be written in terms of these guys. So you get this kind of expression. So we'll take products of things inside I and then with this kind of thing. But of course, if you consider alpha I times any one of the fw, it still lies inside the augmentation idea. And we already showed that this can be generated as a left module by the alpha i's. So we can write this as summation of some, write fw again of some ij, alpha j. Write the whole thing in this way, so that our expression there, summation gi alpha I times summation fw alpha. So w equals n. This whole thing will be a sum of some gi f w I j alpha I w alpha. Okay, so in particular, so we're done because this will be a word of length n. This has length n plus 1. Sorry. So we proved that in plus 1 can be written, generated as a left module by these guys. There are finitely many of those. In plus 1 is already closed, therefore, so it's also equal to the closure. That's the other session. Corollary. If you take in mod in plus 1, where again, now I can leave out the closure. So this is generated as a ZP module, again this time by the class by Wn alpha, by the words of length n. I guess I should write by the classes mod in plus 1. I guess I should write it this way. Okay. And the proof is, well, we have this exact sequence. 0 goes to I, goes to lambda, goes to ZP, goes to 0. And now we can just take the algebraic tensor product over lambda with I. So what we'll get is I tensored with, with in plus 1. With in plus 1 tensored over lambda goes to lambda over I with in, sorry, not in plus 1. In goes to ZP tensored over lambda with in 0. So it's still surjective. And of course, this gets identified. This is tensored over lambda, just algebraically. So this gets identified with in, and the image of this will be in plus 1. is that In mod In plus 1 is just tensor In tensored with Zp over lambda, so that because this was generated as a left